Bismillahirrahmanirrahim. Dear students, have a nice day. Hope you will be fine and best of your health. This is Dr. Sajid Mahmood Rao, Division of Science and Technology, University of Education, Lahore. Today, we are talking about electrophilic aromatic substitution reactions, its applications, and the mechanism for the same. These are the important key concepts which we will discuss in this class session. The electrophilic aromatic substitution reactions, its key mechanisms, and synthetic applications of the organic compounds. Before going to discuss the electrophilic aromatic substitution reactions, let's see the backgrounds of these reactions. As you know, our first guess might be that benzene reacts with chlorine to give an addition product like that shown below, although more slowly than with the normal alkenes. You can see over here in this example the reaction between benzene molecule and chlorine. It gives 1,2-dichlorohexadiene, which is our addition product, in which breakage of carbon-carbon pi bond and formation of two single bond to the carbon atom takes place. Actually, this is our first wrong guess because chlorine gives addition product here which should not be observed. That actually not the product that we observe. Instead, if you treat benzene with chlorine, you will eventually obtain the following product that should be the chlorobenzene instead of 1,2-dichlorohexadiene molecule. So what actually happens? That is substitution, because you can see in this example when the benzene molecule is treated with chlorine, it gives substitution product in which formations of the carbon chlorine bond and breakage of carbon hydrogen bond takes place, but not a nucleophilic substitution reaction since chlorine is not a nucleophile and hydride is not a leaving group. So what bonds formed and what bonds broke in this reaction? We formed carbon chlorine and broke carbon hydrogen. Since the pi bonds are all intact, this is not an addition reaction. Instead, this is therefore a type of substitution reactions where we form and break a bond on a single carbon atom. So we have seen an example of substitution reactions before in our previous semester, but those were nucleophilic substitution reactions, where nucleophile, that may be alkyl sulfide, is added to an alkyl halide, and that is electrophile in the form of alkyl bromide, in which displacing a leaving group that should be bromide as an anion here and forming a carbon nucleophile bond that should be carbon sulfide in this case maybe takes place, and breaking a carbon leaving group bond that may be carbon bromide bond here is takes place. So is the reaction of chlorine with benzene like a nucleophilic substitution reactions? No. Chlorine is an extremely poor nucleophile, reacting as an electron donor only with the strong Lewis acids, that is aluminum trichloride, as we see in the next examples. When combined with even a relatively mild nucleophile such as the pi bond in an alkene, it behaves as an electrophile, electron acceptor, as we saw in its reactions with the alkenes. The reaction of chlorine with benzene is thus called an electrophilic aromatic substitutions, which can be represented as EAS for a short term. Electrophilic because we are adding an electron poor species, that is electrophile, to an aromatic compounds, that is benzene, and substitution stands for because we are breaking carbon hydrogen bond and forming Ce bond, where E is our electrophile, that may be chlorine atom in this case. Let's see the key pattern for 6 important electrophilic aromatic substitution reactions. In this section, we will introduce these 6 key electrophilic aromatic substitution reactions, which group nicely into 3 pairs, that is chlorinations and bromination, nitration and sulfonation, Friedel-Crafts alkylations and Friedel-Crafts acylation. We are not going to get into the mechanism here yet. The point here is just to follow what bonds form and break so that you see the key pattern of these reactions. You can see over here in this table the 6 key reactions of electrophilic aromatic substitutions, in which we can observe the key pattern of benzene molecule with that of the electrophiles. In this case, the benzene molecule is treated with electrophile in the presence of Lewis acids. We obtain electrophilic aromatic substitution product, in which key bond that is formed is carbon electrophile bond, and key bond that is breakdown is carbon hydrogen bond. Let's see different kinds of electrophiles that can react with benzene molecule and give different kinds of the substitution product of the benzene molecule. So when we take chlorine as an electrophile in the presence of Lewis acid, that may be AlCl3 or FeCl3, and chlorine is taken or behaves as an electrophile, this reaction corresponds chlorination. So when we take bromine as an electrophile in the presence of Lewis acids, that may be aluminum tribromide or FeBr3, in which bromine behaves as an electrophile, this reaction generally known as bromination. When we take nitric acid as an electrophile in the presence of Lewis acid, that may be protonated sulfuric acid, and nitronium ion behaves as an electrophile, these reactions represented as nitration. When we take sulfur trioxide as an electrophile in the presence of Lewis acids, that may be protonated sulfuric acid, and protonated sulfur trioxide behaves as an electrophile, these reactions corresponds sulfonation. When we take alkyl halides as an electrophile in the presence of Lewis acids, that may be aluminum trichloride, FeCl3 or others, and alkyl behaves as an electrophile, the reaction represents Friedel-Crafts alkylation. And finally, when we take acyl halide as an electrophile, in which aluminum trichloride and FeCl3 is used as Lewis acids, and acyl group behaves as an electrophile, this reaction is known as Friedel-Crafts acylation. So we can say the Lewis acids accelerate the rate of electrophilic aromatic substitution reactions. Let's see how this reaction is accelerated by the Lewis acid. The reactions of chlorine with benzene is faster than toenail growth, but not by much. It is, however, much faster with more electron-rich aromatics such as toluene and phenol. So instead of sitting around the lab for weeks waiting for reactions to complete, we can add a reagent that soups up the reactivity of the chlorine to make it into an even better electrophile, that is a catalyst, in other words. Addition of good Lewis acids like AlCl3 or FeCl3 does the trick. There are many other Lewis acids which will also do the job, but that's a topic for when we get into the mechanism. So we can prove it with the example of chlorination, in which the reaction of chlorine with benzene is slow. The Lewis acids such as aluminum trichloride or FeCl3 greatly accelerate the rate of chlorinations. In this example, the reaction of benzene molecule is carried out with chlorine atom in the presence of AlCl3. We can also use here FeCl3 among others, and we obtain a substituted chlorinated benzene molecule, in which the bond formations is carried out between carbon and chlorine, and bond breaking is carried out between carbon and hydrogen atom. Let's see how does this work in the next slide. From our series on alcohols, you may recall that alcohols can be coaxed to precipitate in the substitutions and elimination reactions if a strong acid is added, that forming protonated alcohol. That's because the conjugate acid is always a better leaving group. Water is a weaker base and thus a much better leaving group than hydroxyl group. So when the ethanol itself will never react with sodium chloride to give ethyl chloride, because the resulting leaving group hydroxide ion is too strong a base relative to chloride ion for the reaction to proceed to any extent. But if we convert the alcohol into its conjugate acid, that is protonated alcohol, with a strong acid such as hydrochloric acid. The reactions can then proceed since chloride ion is displacing the much weaker base, that is water. Let's see how alcohol is protonated with hydrochloric acid. It can be helpful to think of proton as a weakening the CO bond and thus making the carbon attached to it a better electrophile. You can see over here in this example, when alcohol is treated with hydrochloric acid, here the lone pair electrons of the hydroxyl group abstract the protons from the hydrochloric acid and become protonated, which reacts much more quickly with the nucleophiles than the simple alcohol molecules, because there is a weaker CO bond as compared to the previous one in the reactant site. So the hydroxyl group is easily removed in the form of water molecules than the simple hydroxyl group. So just as acid primes the carbon attached to the hydroxyl group for a subsequent reactions by converting the hydroxyl group into its conjugate acids, Lewis acid similarly work the same magic on the chlorine atom. And for that matter, all the electrophilic aromatic substitution reactions we will be covering will involve some kind of acid catalysis. In the case of chlorination, the Lewis acid, that is aluminum trichloride, in the next slide example, accepts a pair of electrons from chlorine. This weakens the chlorine-chlorine bond, making it into an even better nucleophile. Attack by a nucleophile at the distal chlorine will liberate not chloride as an anion, but the even weaker base and thus the better leaving group, that is aluminum tetrachloride, as an anion. Let's see how the Lewis acid, that is aluminum trichloride, converts the chlorine molecule into much better electrophile than chlorine molecules. So you can see over here in this example, the lone pair electrons of the chlorine molecule donates it to the electron deficient species, that is aluminum atom within the aluminum trichloride, making it much better electrophile than chlorine in the form of intermediate, in which we can observe a weaker chlorine-chlorine bond. So additions of a Lewis acid, which recall includes Bronsted acids like concentrated sulfuric acid, is a common thread in the 6 key electrophilic aromatic substitution reactions, which are generally covered in the introductory organic chemistry. Now come to the real topic, that is electrophilic aromatic substitution reactions. So let's see the statement of these reactions. The introducing of a wide variety of electrophilic reagents to the benzene molecule by the replacement of the proton under suitable conditions referred to as electrophilic aromatic substitution reactions. In the example, you can see over here, the pi electrons of the benzene molecule make a bond to the incoming strong electrophile, and we can observe a substituted benzene molecule in the product side by the removal of a proton, and we get the substituted benzene molecule. Let's see the energy profile diagram of electrophilic aromatic substitution reactions. As you know, we have a graph between energy and reaction coordinates. We have energy in the y-axis and reaction coordinate, that is time, in the x-axis. First, the overall appearance is determined by the number of transition states in the process. As you know, the transition state always have partial bonds and are at the peaks of a reaction's energy diagram, and intermediates such as carbocations are in the valley between two peaks. Intermediates can be isolated and observed. However, in contrast, the transition state have a lifetime of femtoseconds and cannot be isolated. Electrophilic aromatic substitution reactions has two steps: attack of the electrophile and deprotonation, which each have their own transition state. There is also a carbocation intermediate. This means that we should have a double humped reaction energy diagram. Second, the relative heights of the peaks should reflect the rate limiting step. As you know that electron donating substituents increase the rate of reactions, that is activating, and electron withdrawing substituents decrease the rate of reactions, that is deactivating. Conversely, substitutions of hydrogen for deuterium has very little effect on the rate reactions, which leads to us conclude that the second step is not rate determining. Since electron donating and electron withdrawing substituents affect the nucleophilicity of the pi bond as well as the stability of the intermediate carbocation, the logical conclusion is that attack on the electrophile step 1 is the rate determining step. We therefore should conclude that the higher hump in our reaction energy diagram representing its higher activation energy. Let's see some important key points for electrophilic aromatic substitution reactions which are helpful to develop the key mechanism of electrophilic aromatic substitutions process. As you know, the benzene has pi electrons. The pi electrons of benzene have an ability to attack on strong electrophile, resulting a carbocation is generated upon benzene molecule. The carbocation stabilizes itself by resonance phenomena. This carbocation is called sigma complex because the electrophile is joined to the benzene by a new sigma bond. The sigma complex is called arenium ion. This sigma complex regains aromaticity by two ways. First, by reversal step, and the second by a loss of proton. In this way, to lead the substituted product. Let's see the key mechanism of electrophilic aromatic substitution reactions. In the first step of electrophilic aromatic substitution, which resembles the addition of electrophiles to the alkenes, the electrophile accepts a pair of electrons from the aromatic ring. However, because this electron pair forms a part of delocalized aromatic sextet, aromatic compounds are significantly less reactive than alkenes. They are so much less reactive that Lewis acid, such as FeBr3 in bromination and AlCl3 in alkylations and acidation, in which there is required as a catalyst to generate an electrophile that is potent enough to react with the aromatic ring. When the electrophile adds to the aromatic ring, it produces a carbocation intermediate. The first step of the electrophilic aromatic substitution is usually the rate determining step. Because a new sigma bond forms in the first step, the intermediate is called a sigma complex or an arenium ion. This carbocation is resonance stabilized but is not aromatic because it has only 4 2p electrons. Therefore, the sigma complex is much more reactive than the original aromatic ring. The formations of the sigma complex in electrophilic aromatic substitution of a benzene ring has a higher activation energy than electrophilic additions to an alkenes. Therefore, the rates of electrophilic aromatic substitution reactions are slower than the rates of electrophilic additions reactions to alkenes for the same electrophile. For example, bromine reacts instantly with the alkenes but does not react at all with benzene except in the presence of a strong Lewis acid catalyst. In the faster second step of the electrophilic substitution mechanism, the proton bound to the sp3 hybridized ring, that is carbon atom, leaves, restoring the aromatic pi system a nucleophile acting as a base and extracts the leaving proton to form the final substituted electrophilic benzene molecule. Electrophilic aromatic substitution reactions have rich and synthetic applications in the field of chemical industries, pharmaceutical sectors, agrochemical industries, pesticides, polymer industries, paints, dyeing, synthetic rubber, detergents, food and resins and cosmetic industries. Now we discuss the use of some common organic synthetic compounds. The first molecule is chlorobenzene. The major use of chlorobenzene is an intermediate in the productions of commodities such as herbicides, dyestuffs, and rubber. Chlorobenzene is also used as a higher boiling solvent in the manufacture of adhesive, paints, paint removers, polishes, dyes, and pharmaceutical drugs. The second molecule is nitrobenzene. Nitrobenzene is used to manufacture aniline. Nitrobenzene is also used to produce lubricating oils such as those used in motors and machinery. A small amount of nitrobenzene is used in the manufacture of dyes, pharmaceutical drugs, pesticides, and synthetic rubber. The next molecule that is synthesized by using electrophilic aromatic substitution reactions is benzene sulfonic acid. It is used in the formation of detergents, laundry powders, dishwashing liquids, drugs, multiple syntheses. It's also used as degreasers in the meat cutting rooms. The next molecule is toluene. Toluene has numerous commercial and industrial applications and is a solvent in paints, lacquers, thinners, glues, correction fluid, and nail polish remover, and is used in the printing and leather tanning process. Methylbenzene can also be used as a fluorine indicator and is a raw material for toluene diisocyanate. The next molecule is acetophenone. Acetophenone is used for fragrance in soaps and perfumes, as a flavoring agent in foods, and as a solvent for plastics and resins. Acute means short-term exposure to acetophenone vapors may produce skin irritation and transient corneal injury in humans. As a solvent, as a solvent and precursor for resins and plastics. It is used in various agriculture chemicals and in grease industries. It is used in lubricants and their additives as well as in olefins. The next molecule is iodobenzene. Iodobenzene is used as analytical reagents and in the manufacture of disinfectants, antiseptics, deodorants, medicines, and other iodine compounds, as well as oxidations of sulfur dyes. They are used in baking ingredients, conditioners, and as animal feed and food supplement for the treatment of their deficiency. Next molecule is anisole. Anisole is used to make perfumes, flavoring, and as a solvent. Anisole is a flavoring agent. Anisole is a precursor to perfumes, insect pheromones, and pharmaceuticals. For example, synthetic anethole is prepared from anisole. The next molecule is trinitrotoluene. TNT is an explosive used in military shells, bombs, and grenades, industrial uses, and in underwater blasting. The next molecule is 2,4,6 tribromaniline. It is used in organic synthesis of pharmaceuticals, agrochemicals, as well as fire extinguishing agents. The next molecule is methyl benzoate. Methyl benzoate is used in perfumery industries. It is also finds it is used as a solvent and as a pesticide used to attract insects such as orchid bees. Nitrochlorobenzene is a common intermediate in the productions of a number of industrially useful compounds, including common antioxidants found in rubber. The last molecule is nitrobenzoic acid. Nitrobenzoic acid is a precursor to 3-aminobenzoic acid, which in turn is used to prepare some dyes. It can be prepared by nitration of benzoic acid. Its salts are very important in the preparation of drug molecules. It has vast applications in research and development areas of pharmaceutical chemistry. Let's see the halogenations of benzene molecule. Benzene reacts with halogens in the presence of a catalyst, replacing one of the hydrogen atoms on the ring by a chlorine or bromine atom. The reactions happen at room temperature. The catalyst is either aluminum chloride, aluminum bromide, if you are reacting benzene with bromine, or iron. Here, strictly speaking, iron is not a catalyst because it gets permanently changed during the reaction. It reacts with some of the chlorine or bromine to form iron 3 chloride, FeCl3, or iron 3 bromide, that is FeBr3. These compounds act as the catalyst and behave exactly like aluminum trichloride, aluminum tribromide in these reactions. So, when we see the statement of halogenations, the halogens are substituted with the proton of the benzene molecule in the presence of most commonly Lewis acids, as catalysts by regains aromaticity corresponds halogenations. You can see over here in the example, when the benzene molecule reacts with the halogen atom in the presence of Lewis acids that behaves as catalyst, we get the final substituted halogenated benzene molecule. Now we discuss the types of halogenations. Halogenations includes four types, that are iodination, fluorinations, brominations, and chlorinations. Here we will discuss the iodinations of benzene molecules. Here we will try to understand why iodinations of benzene is difficult by looking at the reaction mechanism, natures of the reactants, and also try come up with a few steps to overcome the challenge. For a faster electrophilic aromatic substitution reactions, any one of the reagent benzene or the halogens in the starting material has to be slightly more reactive than other. For satisfying these conditions, electron donating groups attach to the phenyl ring, making it more electrophilic or preferred over the unsubstituted benzene molecule. Also, the electrophilicity of the halogens is increased by using Lewis acid catalyst, thereby making it more reactive. These changes in turn help to achieve transition state faster and stabilize it better. For the halogens, the electronegativity and the electrophilicity decreased from fluorine to iodine in the periodic table. Fluorine is most electrophilic and iodine is least. Therefore, fluorination is highly reactive and iodination is highly unreactive for electrophilic aromatic substitution reactions. The exothermic rates of aromatic halogenations also decrease from fluorine to iodine. Fluorination reactions being highly exothermic and explosive, the reactions cannot be controlled, resulting in polyfluorinated products. For iodination, the reaction is endothermic with 12 kJ per mole of energy absorbed. Therefore, it cannot be done using the conventional method using Lewis acid catalyst and requires strong oxidizing agent. So, the iodination of benzene is that in which the introducing of iodine cation to the benzene molecule by the replacement of the proton in the presence of nitric acid, which is used as an oxidizing agent referred to as iodinations. In the example you can see over here, the benzene molecule is treated with iodine molecule in which iodide plus is behaved as an electrophile in the presence of nitric acid, that is used as oxidizing agent, and we get the final substituted benzene molecule, that is iodobenzene, by the formation of byproducts, that is nitrogen oxide and water molecule. Let's see the important key points which are helpful for the key mechanism of iodinations and applications of iodobenzene. Iodine is very less reactive reagent, so the iodine electrophile cannot introduce directly. Iodination is carried out by indirect method by using nitric acid as an oxidizing agent. Nitric acid converts iodine 0 oxidation state to iodine plus oxidation state, which is better electrophile for the said reaction mechanism. Iodobenzene is used in various carbon-carbon coupling reactions. It can be used in the preparation of iodobenzene dichloride, which is employed as an oxidant to oxidize alcohols to carbonyl compounds and as a chlorinating agent. The key mechanism of iodination consists of three steps. In the first step, that is preliminary step, the formations of the electrophile, that is iodide ion, is carried out. In this step, the iodine molecule is treated with nitric acid. The nitric acid behaves as an oxidizing agent which convert iodine 0 oxidation state to iodine plus oxidation state. In this way, we get the iodide as an electrophile by the formations of nitrogen oxide and water molecule. In second step, The pi electrons of the benzene molecule attack on the strong electrophile, that is iodide, as an electrophile to form a sigma complex. In the sigma complex, there is a formation of electron deficient carbon which stabilizes itself by using resonance phenomena. The sigma complex is also known as adenine ion. In third step, deprotonation regains aromaticity and gives the substituted product. Here, water molecule behaves as a base and it abstracts the protons from the electron deficient benzene molecule. In this way, a bond that is formed once between the carbon and the hydrogen shift back towards electron deficient benzene molecule and generate the iodobenzene substituted product by the formation of side product, that is hydronium ion. Fluorination of benzene molecule. Let's see how fluorination is carried out with the benzene molecule. The controlled fluorination of benzene is difficult, but it can be accomplished by indirect method using a mixture of sodium nitrite and hydrochloric acid via diazonium salt of aniline molecule, resulting in the formations of fluorobenzene. You can see over here in the example, if the benzene molecule is simply treated with the fluorine, we get the fluorobenzene, but these reactions cannot proceed. In the second example, you can see when the benzene molecule is treated with fluorine, we can get multi-substituted product that may be hexafluorobenzene molecule. So, fluorination of benzene is carried out in the presence of nitric acid and hydrochloric acid via diazonium salt of the aniline molecule. In this way, we can achieve the final fluorinated benzene molecule product. These are the important key points that is relevant to the fluorination of benzene molecule. The fluorine electrophile cannot easily generated because it shows vigorous reaction. A mixture of sodium nitrite and hydrochloric acid is used by which diazonium salt is produced and the reaction is carried out smoothly. Simple fluorination goes to multi-substituted benzene molecule. Diazonium salt of benzene further treated with tetrafluoroboric acid, and finally upon simple heating we get fluorobenzene. Let's see the key mechanism of fluorobenzene. It consists of the following steps. Initially, the aniline molecule is treated with sodium nitrite that is used as oxidizing jet in the presence of hydrochloric acid. In this way, we get the first intermediate, that is benzene diazonium chloride. This intermediate is further treated with tetrafluoroboric acid and we get benzene diazonium cation. The benzene diazonium cation on simple heating give fluorobenzene molecule by the evaluations of nitrogen as a gas. Fluorobenzene is used to control carbon content in steel manufacturing. It is an intermediate for pharmaceuticals, pesticides and other organic compounds. Dear students, these are assignments and quiz which you would have to submit within 7 days after the delivery of this lecture. The first assignment is how electrophilic aromatic substitution reactions are important for the synthesis of organic compounds. Draw its key mechanism. How much is it applicable in the industrial sector? The second assignment, the formyl group cannot introduce to the benzene by Friedel-Crafts acylation in the usual manner. How can it be accomplished? Draw its mode of mechanism and applications. Thank you.